Welcome to the third tutorial on quantitative analysis using the STATA software. Now I am going to show how to check the heteroscedasticity and multicollinearity issues. For that purpose, before applying the command to check the multicollinearity, we have to give command for normal pooled OLS regression. So I am going to give the command for normal pooled OLS regression. Although the data is in panel nature, but for the purpose of checking the multicollinearity, I have to give command for normal regression, which is known as pooled OLS. The command is reg. Then give input the dependent variable, then provide the independent variable. Here reg indicates the regression, which is pooled OLS regression, and ROE is the dependent variable, and natural logarithm of CSR, this is the independent variable, and this is another independent variable which is also known as control variable. So for the purpose of checking the multicollinearity, I am going to find out the normal pooled OLS regression. So this is the output for the pooled OLS regression, where you can see the coefficients of the variable, where this is the ROE, which is the dependent variable. We can see all the variables are in significant position for this model. Now I am going to check whether there is any multicollinearity issue in these variables. The command is stat VIF, then pressing enter. Here we can see the coefficients of the BIF. The standard accepted value is greater than 1 and less than 2. We can see the BIF value is showing 1 for both of the data. That's why we can say that there is no multicollinearity issue, because the BIF value is showing greater than 1 and less than 2. Now I'm going to check whether there is any heteroscedasticity problem in the variables or in this model. For that purpose, the command is stat head test. So this is the command by which we can get the result for the heteroscedasticity test. From the output of the heteroscedasticity test, we can see the null hypothesis is there is a constant variance, and this null hypothesis can be rejected whenever there is a high chi-square value. But in our case, we can see the chi-square value is very low. That means there is a constant variance. That means we cannot reject the null hypothesis. That means in this model there is no heteroscedasticity problem. So we can say that the command for testing the heteroscedasticity is stat head test, and where if the chi-square value is low, then there is no heteroscedasticity problem. But if the chi-square value is too much high, in that case we can say that there is a heteroscedasticity problem. But in our case, there is no heteroscedasticity issues in our model. Although there is no heteroscedasticity problem in our model, but suppose there is a heteroscedasticity, in that case what should you do to avoid the heteroscedasticity problem? In that case, whenever you are going to regress the dependent variable with the independent variable, you have to give a extra command which is robust. So although there is no heteroscedasticity in our data, but suppose there is a heteroscedasticity, in that case you can give this command whenever you are going to find out the pooled OLS regression to avoid the heteroscedasticity problem. So this is the command by which you can avoid the heteroscedasticity problem. But in our data there is no heteroscedasticity issues, but I have given the instructions by which you can utilize if your data have the heteroscedasticity issue. In the same way, suppose your data has a autocorrelation problem, and to avoid the autocorrelation problem from your model, you can give command cluster, then in the bracket you can indicate the ID to avoid the autocorrelation problem. But in our data, maybe there is no autocorrelation problem, but suppose there is a autocorrelation problem. In that case, whenever you are going to do the old OLS regression, then this is the command reg, then dependent variable, independent variables, comma, cluster ID. By this command, you can avoid the autocorrelation problem from your model. So this is the output which is avoiding the autocorrelation problem.